NASA has invested approximately $25 billion over more than a decade in the Artemis program, with Artemis II planned to send 4 astronauts around the Moon. But instead of rushing to land on the lunar surface next, the space agency made a shocking announcement that surprised even veteran space watchers. They're adding an entirely new mission that will test lunar landers in Earth orbit first, while simultaneously canceling billions in rocket upgrades and promising to land humans on the Moon every 6 months by the early 2030s. NASA has announced adjustments to the Artemis timeline, with current administrator Bill Nelson leading program communications that abandons the original plan to land directly on the Moon after Artemis II. The new architecture adds Artemis III as a low Earth orbit docking test in mid-2027, pushes the actual lunar landing to Artemis IV in early 2028, and commits to a $30 billion 3-phase moon-based construction plan. But this isn't just about delays. NASA is accelerating mission frequency from every 3.5 years to every 10 to 12 months, while international partners from Japan, Europe, and Canada contribute everything from pressurized rovers to complete habitat modules. The question isn't whether NASA can return to the Moon. The question is whether they can build the infrastructure to stay there permanently. Artemis II is currently scheduled for late 2025, with mission duration planned for approximately 10 days around the Moon. NASA faced a choice: rush toward a high-risk landing attempt or build capability step by step. The agency chose the methodical approach, announcing that Artemis III would become a low Earth orbit systems test rather than the triumphant lunar landing originally planned for 2027. NASA Associate Administrator Amit Kshatriya explained the reasoning as a step-by-step buildup of capability, with each step bringing us closer to our ability to perform the landing missions. This mirrors Apollo 9 in 1969, when astronauts tested lunar module docking in Earth orbit before Apollo 11 attempted the surface landing. NASA continues development of the Space Launch System Block 1B upgrade, including the exploration upper stage, though the program has experienced delays and cost increases and hundreds of millions in annual sustainment expenses. The Block 1B upgrade is designed to increase lunar payload capacity from approximately 27 to 38 metric tons, but had experienced repeated delays and technical setbacks. By standardizing on the existing Block 1 configuration, NASA can launch every 10 to 12 months instead of waiting 3.5 years between missions. This acceleration serves a specific purpose: maintaining the civil servant workforce skills that atrophy during long gaps between launches. The decision reflects a fundamental shift from complex, multi-capable mission designs toward what NASA calls focused, phased architecture that builds capability landing by landing, incrementally. Commercial lunar landers from SpaceX and Blue Origin also needed additional development time, making Earth orbit testing a safer option than debugging systems during a high-profile first landing attempt. Artemis III in mid-2027 will send 4 astronauts to low Earth orbit for approximately 10 days, where they'll dock with one or both commercial lunar landers. SpaceX will launch a Starship HLS variant directly to Earth orbit, where it arrives with enough propellant to conduct rendezvous maneuvers, station keeping, and test burns before safely deorbiting. This eliminates the complex orbital propellant transfer operations that were central to the original Starship lunar concept, requiring only tens of meters per second of velocity change instead of the 3.2 kilometers per second needed for translunar injection. NASA hasn't ruled out testing both landing systems during the same mission, creating a direct competitive demonstration between SpaceX's Starship HLS and Blue Origin's Blue Moon Mark II lander. The mission will test rendezvous and docking procedures, life support systems integration, communications protocols, and the new Axiom Space extravehicular activity suits in an operational environment. The Axiom Extravehicular Mobility Unit represents a complete redesign from current spacewalk equipment, functioning as what engineers call a one-person spacecraft with autonomous life support and radiation protection. Rather than waiting until the risky Artemis IV landing to test these advanced suits, Artemis III provides a controlled environment where any issues can be identified and fixed. From an engineering perspective, Artemis III dramatically simplifies mission requirements: no translunar injection, no lunar orbit operations, and no permanently shadowed region navigation challenges. The mission serves as a final systems checkout before committing to the actual lunar landing, where rescue options are limited and mission stakes are exponentially higher. Both commercial landers will demonstrate their ability to dock with Orion, maintain thermal control of cryogenic propellants, and execute precise orbital maneuvers that will be required during lunar operations. Artemis IV in early 2028 will end a gap of more than 55 years since humans last walked on the Moon, when Apollo 17 landed in December 1972. 4 astronauts will launch on the SLS, travel to lunar orbit, and dock with a commercial lander that will carry 2 crew members to the surface near the South Pole for approximately 7 days. NASA has identified 9 candidate landing regions, all concentrated at the lunar South Pole, where permanently shadowed craters may contain water ice deposits that have persisted for billions of years. These permanently shadowed regions maintain surface temperatures below 110 Kelvin, approximately -163 degrees Celsius, creating cold traps that preserve volatiles. The South Pole presents challenges that didn't exist during Apollo missions at lower latitudes. Earth is only visible for approximately 2 weeks each lunar month, requiring strong surface communication networks. This communications challenge became clear during the Intuitive Machines IM-2 lander mission, which experienced telemetry loss during descent and landed sideways in a crater due to intermittent Earth contact. NASA planetary science researchers have explained the scientific rationale. The Moon's South Pole is a completely different environment than where we landed during the Apollo missions. It offers access to some of the Moon's oldest terrain, as well as cold, shadowed regions that may contain water and other compounds. The astronauts will wear the Axiom extravehicular mobility units tested during Artemis III, conducting field geology, sample collection, and deploying scientific experiments across the polar terrain. Surface mobility will initially depend on astronaut walking range, but NASA is developing the Lunar Terrain Vehicle with 3 companies: Intuitive Machines, Lunar Outpost, and Venturi Astrolab. NASA has awarded Lunar Terrain Vehicle contracts to multiple companies, with total program costs still being determined, and represents the first crewed lunar rover since the Apollo lunar roving vehicles. NASA hasn't yet selected whether SpaceX's Starship HLS or Blue Origin's Blue Moon Mark II will carry the Artemis IV crew, maintaining competitive pressure on both contractors. The mission duration of 7 days balances scientific objectives with life support constraints and crew tolerance limits for the first landing attempt. Samples and data collected during Artemis IV will directly inform the location and design of the permanent moon base infrastructure deployed during subsequent missions. NASA has outlined a 3-phase, $30 billion architecture to establish permanent human presence on the Moon between 2027 and 2036. Phase 1, Build, Test, Learn, runs through 2028 with a $10 billion investment, accelerating commercial lunar payload services deliveries to 21 robotic landings by the end of 2028. These robotic missions will transport rovers, power generation equipment including radioisotope thermoelectric generators, communications nodes, navigation infrastructure, and scientific payloads to prepare for human habitation. The Viper rover mission was canceled by NASA in July 2024 due to cost and schedule concerns. Will execute a 100-day surface science mission investigating water ice deposits using a neutron spectrometer and core sampling system capable of drilling 60 centimeters deep. Phase 2, Establish Early Infrastructure, spans 2029 through 2032 with another $10 billion, incorporating major international contributions. Japan Aerospace Exploration Agency will provide a pressurized rover allowing astronauts to work without spacesuits, extending mission duration and scientific productivity. The European Space Agency contributes the Lunar IHAB International Habitat, one of 2 primary habitation modules where astronauts will reside and conduct research. The Canadian Space Agency provides the Lunar Utility Vehicle and robotic interfaces, while Italy's Space Agency contributes multi-purpose habitats. Phase 3, Enable Long-Duration Human Presence, runs from 2033 through 2036 with the final $10 billion investment. Cargo variants of Starship HLS and Blue Moon landers, with payload capacities of 30,000 kilograms or more, will deliver power systems, life support infrastructure, and oxygen production equipment. NASA targets semi-annual crewed missions by Phase 3, with potential to increase frequency as capabilities mature. The total $30 billion investment must be understood against the backdrop of current mission costs, Each full Artemis mission costs approximately $4 billion. 2 missions per year at current cost levels would rapidly exceed the phase budgets, indicating that significant cost reduction through commercial transition must occur in parallel. International partnerships distribute both technical responsibility and political commitment across multiple national space agencies, mirroring the International Space Station model. The Gateway lunar outpost will orbit in a near-rectilinear halo orbit, providing fuel-efficient access to the lunar surface while maintaining continuous communication with Earth throughout its 7-day orbital period. This orbit hangs almost like a necklace from the Moon, balancing between Earth's and the Moon's gravitational influence for maximum efficiency. The Capstone CubeSat, launched in 2022, validated this orbital mechanics before Gateway's deployment. 2 fundamentally different engineering philosophies compete to carry astronauts back to the lunar surface: SpaceX's Starship HLS and Blue Origin's Blue Moon Mark II lander. SpaceX's Starship HLS removes the heat shield and flight control surfaces from the standard Starship, reducing dry mass for greater payload capacity or extended lunar loiter capability. The vehicle uses 6 Raptor engines burning liquid methane and liquid oxygen, but transitions to high-thrust landing engines in the mid-body section during final descent to avoid surface plume impingement. Starship HLS can remain in lunar orbit for up to 100 days while maintaining thermal control of cryogenic propellant tanks through specialized insulating tiles. The operational concept requires multiple propellant transfer operations with Starship tanker spacecraft in Earth orbit, with SpaceX estimates requiring multiple tanker flights for lunar missions, with exact numbers still being refined through testing. These cryogenic orbital refueling operations have never been demonstrated in spaceflight, representing a critical technology gap that SpaceX must resolve before Artemis IV. SpaceX received a fixed-price contract valued at $2.89 billion in April 2021 for initial HLS development and 2 operational flights. Blue Origin's Blue Moon Mark II employs a more traditional architecture with a separate ascent stage using 3 BE-7 engines burning liquid hydrogen and liquid oxygen. The Blue Moon system incorporates a separate cislunar transporter designed by Lockheed Martin, launching on United Launch Alliance's New Glenn rocket for orbital assembly operations. This approach separates the refueling function into a dedicated vehicle, contrasting with Starship's single-vehicle architecture. Blue Moon Mark II can carry up to 4 astronauts for 30 days on the lunar surface in fully reusable configuration, with cargo variants capable of delivering 30,000 kilograms on one-way missions. Blue Origin was selected for the Sustaining Lunar Development contract in May 2023, with contract value reported as approximately $3.4 billion. NASA has not yet selected which system will carry the Artemis IV crew in early 2028, maintaining competitive pressure on both contractors. The agency explicitly hasn't ruled out testing both systems during Artemis III, creating a direct performance comparison before committing to either provider for the actual landing. The Artemis program has evolved from a simple return to the Moon into the foundation for permanent human presence beyond Earth, but the path forward depends on resolving technical challenges that have never been attempted. Cryogenic propellant transfer in orbit, South Pole communications networks, and international coordination across multiple space agencies represent engineering and political hurdles that could derail the timeline. NASA's decision to test systems in Earth orbit first, accelerate mission frequency, and standardize on existing hardware reflects lessons learned from both Apollo successes and recent program delays. The $30 billion moon base plan spans 3 phases over 10 years, but current mission costs of $4 billion each suggest that commercial cost reduction must succeed for the architecture to remain affordable. If successful, NASA will transition from government-developed single-use missions to commercially operated reusable systems that could enable lunar landings every 6 months by the early 2030s. The next 18 months will determine whether humanity returns to the Moon temporarily or establishes the infrastructure to stay permanently. Artemis III's Earth orbit test in 2027 will provide the first real answer.